So when we're reacting a strong acid with a strong base, or any acid with any base, we can construct what we call a pH titration curve. So if you think back to the first semester, we talked about titrations a little bit. So titration is a way of determining the concentration of a solution by reacting a known volume of one solution with another substance. And the other substance we know the concentration of. So if we know the volume we started with of the first substance, and then we know the concentration and volume of our other substance, we can put those together and do some unit conversions here to figure out the concentration of our unknown. So we would have our unknown solution that is of a known volume in a flask, and we would have our solution that we know the concentration of in a burette. And we can determine the volume of this known solution that we had, so we can then calculate the concentration of our unknown solution down here. So we reach a point where we have added a stoichiometrically equivalent quantity of the acid and the base. So the stoichiometric equivalent quantity means we've added the same number of moles of acid that we have of base, and we call that our equivalence point. So if we do this using a pH meter, we can actually determine the pH as we're moving along. So we have a point where we just have, for example, if we're titrating hydrochloric acid with sodium hydroxide, we have a point here where we just have hydrochloric acid and we have our pH of that. And then after we add enough base, we're adding base to our acid, we start to raise the pH a little bit, and we eventually get to a point where the pH starts to stabilize here, and we see a point where the pH is going up rather rapidly. But it happens right at this volume. So this volume where we have a rapid increase in the pH is what we call our equivalence point. This is the point where we've added enough of the base to neutralize our acid. And if we have our long stretch here where the pH increases rapidly, right in the middle of that is our equivalence point, and that's at a pH of 7. So that would make sense. We're adding a strong acid to a strong base, so if we've neutralized that, we just have sodium chloride and water at this point. So we should have a pH of around 7. If we continue to add sodium hydroxide past that equivalence point, we'll then increase the pH into a basic pH. So before the addition of any sodium hydroxide, we just have the pH of our hydrochloric acid, which is what we were pointing out on the previous graph. And we're adding some sodium hydroxide, but we haven't gotten to the point where we've neutralized it, so we still have more of the acid. Then we reach a point where the amount of H3O plus is equal to the amount of OH negative, so the pH should be 7. And then we can get to a point where we have excess hydroxide. So let's look at a situation where we want to know how much sodium hydroxide to add to a certain quantity and concentration of hydrochloric acid. So we want to know what volume of sodium hydroxide will be required to reach the endpoint. And we know our concentration of sodium hydroxide, and we know our concentration of hydrochloric acid. So remember, molarity means moles per liter. So this means that I have 0.200 moles of sodium hydroxide per 1 liter solution. So if you think back to how we did calculations with titrations, we always start with the one that we know everything about, and we work towards the one where we have something that's unknown. So we start with the 40 milliliters of 0.100 molar hydrochloric acid. So we have 40.0 milliliters of hydrochloric acid. And since molarity is moles per liter, we'll need to convert milliliters into liters. So we have 1,000 milliliters of hydrochloric acid per 1 liter of hydrochloric acid. And then 0.100 molar tells us that for every 1 liter of hydrochloric acid, we have 0.1 moles of hydrochloric acid. And then if we write out our reaction, so hydrochloric acid plus sodium hydroxide, this is an acid-base neutralization, so that's going to give us water and sodium chloride. So hydrochloric acid and sodium hydroxide react in a 1-to-1 ratio. So we have 1 mole of hydrochloric acid reacts with 1 mole of sodium hydroxide, and then our 1 mole and then our sodium hydroxide is 0.2 molar, so 0.200 moles of sodium hydroxide, run out of room here, for 1 liter of sodium hydroxide. So if you put that into your calculator, 40 times 0.1 divided by 1,000 times 0.2, we get 0.020 liters of sodium hydroxide. Or if we convert that to milliliters, we get 20 milliliters of sodium hydroxide. The second part of this question asks us, what will the pH be at the endpoint? Well, since we're reacting a strong acid with a strong base, and we get water and some dissolved salt, the pH should be 7 at the endpoint. So we don't have anything we need to calculate for the pH. We just have to recognize that we're reacting a strong acid with a strong base. So that should give us water and a salt that's dissolved in water. So we should have a pH pretty close to 7. So we're going to stop here, and we will pick up with some more calculations in class.